Yeah.
All right, we're going to go ahead and get started a little early since they won't let anybody else in anyway. So I'm Doug Davis, track host, but obviously you're here to hear Mikkel talk about operators. I was actually reviewing the proposals for the CFPs for this thing. Operators was one of the hottest topics out there. So obviously, as you guys are a testament, this is obviously a very, very exciting topic. So this should be really good. One quick reminder: please rate the talk when you're done through the app. That way the organizers know whether it was a popular topic, speaker did well or not, that kind of stuff. Leave as many comments as you possibly can. And with that, there you go.
Thank you, Doug. So welcome everyone who could get into my talk. It's about ES Operator, which is an open source project for running Elasticsearch, like running big scale Elasticsearch, and how we run it in Kubernetes. At Zalando, and I want to go through a story of how we built this operator, and I think the patterns here also apply to other applications, not only Elasticsearch, but also Cassandra, Kafka. These kind of applications can also benefit from this pattern, I think. So who am I? I'm Mikkel Larsen. I am a software engineer at Zalando. I work at the cloud infrastructure team, which deals with Kubernetes, AWS infrastructure. So we manage a bunch of clusters, and we were in a joint effort to develop this Elasticsearch operator between the search department and our team. So we came with the Kubernetes knowledge, and they came with the Elasticsearch knowledge. So I'm not an expert on Elasticsearch. I know some things, but if you really want to know this, then I will forward you to some colleagues who are unfortunately not here at the conference. If you want to tweet at me saying that it's stupid to run our most critical stateful applications on Kubernetes, then you're welcome to do that. But maybe you have a different opinion after the talk. Let's see. What is Zalando? We are Europe's leading online fashion platform. We sell socks and shoes and all kinds of fashion articles all over Europe online, and you go there, you order your things, get them, and then you can send them back if you don't like it, all for free. And we are in 17 markets. We have a revenue of 5.4 billion, so quite a big company, 26 million active customers. We are 15,000 employees in Europe, and roughly a little under 10% of these are working within tech, so software engineers and so on. And these are kind of the customers for our team internally. This means that we have a Kubernetes setup at Zalando that looks like this. We declared it the default deployment target this year, meaning that everything that is developed new software has to go to Kubernetes ideally. This means we have 125 Kubernetes clusters right now that we manage in our team, roughly 50% prod, 50% test clusters. This amounts to around 1,400 EC2 instances we run on AWS. This, of course, scales in and out during the day, so it's just a rough number because we have autoscaling with the cluster autoscaler. We started this endeavor with Kubernetes in October 2016, and since then we have updated our clusters from 1.4, the oldest clusters, to now 1.13 last week we rolled out. And we continuously upgrade the clusters, so we don't create new clusters, move workload, we just upgrade them in place. And this, of course, an Elasticsearch operator would also have to take care of this. So what does search look like at Zalando? We have 300,000 products per country, 17 countries. We have 2,000 brands roughly, 700 categories. And all this data is in the Elasticsearch, so you can find it when you go to the website and search for whatever shoes or t-shirts or whatever you like. And this is all powered by Elasticsearch. It has 12,000 RPS or QPS on the normal peak during the week. And we can also handle 8,000 requests per second or updates per second from ingesting the data from the different streams we have internally into the cluster. At Black Friday, which is our biggest commercial event of the year, end of November, we have roughly doubled of what we have on the normal week. And you can see here, we scaled to 512 nodes last Black Friday. This is not on Kubernetes. We just moved it this year, so we will see how it goes, but just to see what the scale is. And normally the workload is not 500, but more like 200 EC2 instances for this Elasticsearch cluster. We have different instance types depending on which country we are serving. They are all part of one big Elasticsearch cluster. But it was running on EC2, AWS with a little bit of tooling around, some bash scripts here and there, some Jenkins pipelines, running quite well, managed by the team, but there was a lot of manual things involved. And considering that we had made Kubernetes the default deployment target, it made sense to move it not only to Kubernetes, but maybe also make some improvements along the way. So goal was move it to Kubernetes. And by moving it to Kubernetes, we had some goals that we wanted to achieve. So we wanted to have safe automatic updates of the Elasticsearch cluster. This means both that Elasticsearch can update, like updating a version of Elasticsearch or changing a configuration of the nodes in the cluster. But it should also handle updates of the underlying Kubernetes cluster. So the way we roll Kubernetes clusters is we scale out the nodes and then move workloads to the new nodes. And this is done all automatically. And the tooling for Elasticsearch has to be aware of this. All the application has to somehow handle this. Another thing was that now we are moving anyway. The old setup in pure AWS was very static. Like we could add manually nodes for like Black Friday, but we couldn't like auto-scale and scale down during the week where we didn't have so much traffic. So actually the cluster was usually scaled to the peak to handle the peak load of the week. And for the whole week, maybe the double amount of nodes that was needed in the night and so on. So we wanted to have advanced auto-scaling to like reduce cost or be able to scale down when the cluster is not used so much. So this was the criteria. We looked into first like how do people run Elasticsearch in Kubernetes. We found the kind of official Helm chart for running Elasticsearch, which is a stateful set. I hope you're all somewhat familiar with stateful sets in Kubernetes. I will not go so much into it, but the idea is that you have a way to say, I want to have X number of pods, and they have some volumes attached potentially, and they have a certain criteria for what is the naming of the pods and so on that you can kind of reliably. And the way it works, if you just take the Helm chart and you, for instance, think of a situation where you need to update the cluster, then the cluster would like want to drain a node. So let's say we have 3 Elasticsearch pods or nodes in the Elasticsearch clusters. The gray are nodes of the Kubernetes cluster, and we want to drain one node. So the tooling will drain a node. This means that we need to delete this pod on the node that is being drained. And what will happen with the Helm chart setup or the stateful set is that it will trigger draining from our infrastructure, basically terminating the pod, as Kubernetes will handle termination normally. Then in Kubernetes you can set a pre-stop hook on the pod definition, which can be like a bash script you can run or whatever. And what it does in the Helm chart is that it excludes the node from the Elasticsearch cluster, meaning that data will not be moved there. So Elasticsearch will stop moving data there and will actually like drain the data away from this node. This we want to do so we don't just drop all the data we had there. If you have volumes, of course, you could have it still attached to a new pod when it comes up, but we also want to make sure that we are not letting any traffic go to this node while we are draining it. So this is kind of why you want to do this. The data is moved, as shown here, and then the pod becomes empty, it doesn't have any data, and then it can be deleted. With this pre-stop hook, you have this thing that the pod is already going into a termination phase. You cannot you cannot stop this in Kubernetes. It's already terminating, and you set the chart sets like a 1 hour delay of the draining. So if your drain takes longer than 1 hour, then you have a problem here. You cannot really handle this. Also, if the bash script doesn't handle network issues or something during the phase, it will just fail maybe, and then doesn't really execute the moving of data correctly. This is one problem with this approach. If we go further, what in the ideal case, when it works, what would happen is a new pod would be replaced by the stateful set on a new node, and this has a post-start hook, which basically removes all these excludes in Elasticsearch, meaning that data can then be moved to the new pod. And Elasticsearch will like rebalance and so on. The problem here is that if you try to autoscale at the same time and you have this pre-start hook which just unblocks all of them, then you could have one pod that is draining and have excluded itself, and then you have another one that just like unexcludes everything, and then it starts to get data again. Of course, you can implement more sophisticated scripts, or maybe writing something in a more advanced language and handle these cases, but it begins to sound like you actually need something like an operator. So the operator pattern it comes in here. I took this from the CoreOS. They kind of coined this phrase operator in 2016, I think. I don't think they like invented the idea, but they kind of called it operator. I think I like this term. And they stated an operator represents human operational knowledge in software to reliably manage an application. So the way I understand it is, you encode like how what you would normally do as a human, kubectl, do this, call drain on Elasticsearch, all these things you incorporate into code that can perform this for you. This is one way I see operators. I also see when I look at what other people are building as operators, operators can also have the functionality of like providing an abstraction. So instead of users defining a stateful set, a service, a volume claim, defining all the, people talking behind me, sorry. Instead of the users defining all these resources and what environment variables to give and so on, you can create an abstraction that like hides all of this for the users. This is not what we focused on. We focused on the purely operational part to start with, because this was really the problem we had. The defining, making user-friendly and so on was not so important, because we are very, like, the team that operates this are very technical and knows a lot about Elasticsearch, so they want to tune it to their liking. But the idea we first had, we call it like BeZero, was to just manage a stateful set in a bit smarter way. So what we could have, what we said was, okay, we cannot modify the replicas directly that you normally have a stateful set, because if you drain a pod, it has this problem that I described before. It just starts terminating, and then you cannot really stop this operation, and if it takes longer than 1 hour, then you cannot handle this case. So we wanted to have it split in like the replicas on the stateful set, and then the desired replicas, which is what the operator tries to achieve. So you might be scaling up, it's easy, you just add another pod, but if you're scaling down, you could have like replicas smaller, the desired replicas, which we put in an annotation. As you can see, it could be smaller, and then the other one could be higher, and then it would eventually like drain and achieve this. We also used update strategy on deletion, which meant that instead of the stateful set controller like modifying and updating the pods when we make an update, the operator can control this process and kill pods once it has drained them. So this didn't really work for us. It was too low level, and like it was complicated to just update the stateful set without, because you have a certain number of replicas in your YAML file, and if you update this, then you override whatever the operator is doing. So this was one thing. And state must be stored in annotation, which is just not nice. It's just a string that you have to then pass, and it just becomes a little bit ugly. It's doable, but yeah. So what we did instead was we thought, okay, we just need some layer of abstraction on top of the stateful set. The stateful set idea is kind of good. It just needs the extra knowledge. So we created something we call Elasticsearch dataset, which is a very thin wrapper. It has this scaling thing for configuring auto-scaling. I will talk about this later. And then it just has replicas like a stateful set, a template for the pod template, so you specify the full thing, and the volume claim template, so you like a stateful set. So this way, anyone can just take a stateful set, modify it a bit, and then they would have it work with their Elasticsearch setup. And this way, we have replicas on the Elasticsearch dataset, and we have also a state on a stateful set, which is managed by the operator underneath. And then we have these two different values that it can reconcile towards. So this is the idea. And from like a higher level, Elasticsearch datasets can either be like a full cluster if you want, but you can also compose them into like one big cluster that consists of different Elasticsearch datasets. And this was what I mentioned in the beginning, that we have different type of instances for the different types of countries, for instance. So Germany is like a lot of traffic we get there, so we have big instances and Elasticsearch dataset for that, this country, and then for other countries we have smaller instance types or smaller pod requests in the Kubernetes case. But they all combine into one big Elasticsearch cluster, which is how the tooling in our search infrastructure works. But you could also have like one set of masters for each of your Elasticsearch dataset. You can kind of compose it like you want, and the operator then manages all these things. So if we look at the example again, like I gave with the stateful set, now with the operator involved, we now have a service created by the operator that like goes into the Elasticsearch API. We have the same pods, and let's think of the same scenario where we have a pod node, a Kubernetes node that is being drained. What the operator does, it detects this because it looks at the label of the node or the status of the node. Okay, it's being drained. Then it scales out the stateful set underneath, so we get an extra pod. So now we have somewhere to move the data from this one we want to drain. Then it calls into Elasticsearch, similar to this pre-stop script would do, and says exclude this particular node from the cluster, so data is moved out of it, and this will then move to the new Elasticsearch node that is available. And once the data is moved, the ES operator can safely delete the pod because now it's completely empty and it's fine to delete it. And then this case is handled, and also like if it takes more than 1 hour, the operator can just continue to try to drain. If the operator dies, it will just start back up and it will just continue from where it stopped. So it's like very resilient in that way. And lastly, the pod is gone. Okay, so this is like the upgrading of a cluster, both Kubernetes and Elasticsearch. We have this operator logic for doing this. And this means that now we have this training logic. It can scale out, it can move the data. Then it's also easy to like add auto-scaling because we have this functionality of draining and so on already. So what we implemented was like custom auto-scaling in 2 dimensions. So we can scale the number of nodes and we can scale the number of replicas inside the Elasticsearch cluster, so the replicas of the shards, of the indices. We looked into using the horizontal pod autoscaler, but it's very, very simple in Kubernetes, and it basically just takes an average of, like if you're scaling on CPU, takes an average over all the pods and then calculate how much would be needed to actually satisfy whatever constraint you set. This is too simple for us because both it's too reactive, like it can be scaling up and down too fast. So we added something like a duration that the CPU has to be above a certain threshold for a certain duration that you configure. And we also have a cooldown, so if you just scale up, the cooldown has to exceed before you can do another scaling action, either up or down. So you don't have this where you scale up and scale down and scale up and move data all around. And in this example, we can scale up. So you see the graph here. It shows like that the CPU is over a certain threshold for some time. We have a very simple case with just 1 node, which is maybe not so safe, but it's very cost efficient, where we have 6 shards. And if we want to scale this up, then we can add 1 new node, and then we can split the shards over these 2 nodes. If we want to scale up further, then we can split it again and have 3 nodes and split the 2 shards on each node. And this way we are reducing the CPU per node, obviously. And if we need to scale further, we can do so. And here we are like limited by, you can set a number of max pods, the max pod you want to have, but we're also limited by the minimum number of shards per node. So if you have 1 as minimum, you obviously cannot go below because then you would get nodes with no shards on it, which is just a waste of money. Also, if you have like a limit of 2, then you would kind of stop here and then you could not scale further. But this you can all configure in the EDS, the Elasticsearch dataset. Similar, if you go the other way, scaling down, the CPU is below a certain threshold for a duration, then we start to scale down to 3 nodes, 2 shards each, and so on all the way down. And here, like the minimum replicas are the boundaries. So if we have a limit of 2 replicas, then it would not scale further than this. And also the max shards per node. So if you have a max of 3, then we could also not scale, even though the minimum replicas might allow it. And then we have another safety, which is max disk uses. And this is to prevent that we scale down, but we have so much Elasticsearch data that we actually will fill up the disk and cause problems that way. So we are also checking into Elasticsearch what are the disk, the uses of the different nodes, and then we check before we do an auto-scaling action if it can actually happen without breaching this boundary. So this is just a safety measure. Another thing is that if something goes wrong, and this is mostly when scaling down, and the cluster is not in green state, the operator backs off and it doesn't do anything. So it just waits for the cluster to be green. Either it can do it by itself, or if an operator, like a human operator, is needed, then they will not do anything until the cluster is green again and someone has, like it might need that you need to do whatever. So this is like another safety to prevent that it messes up the cluster further than it was already. It could be that you're scaling down, then you lose a node because of the cloud provider or whatever at the same time, and then you didn't replicate enough, and you are in a bad situation. But it tries to like protect you as much as possible. The same when doing an upgrade, it will not continue an upgrade if the cluster is not green. So I mentioned there were 2 dimensions for scaling. The other one is like scaling the replicas of the indices in Elasticsearch. So here we have an example where we just have 1 shard, and like adding another node wouldn't do anything because then we just have a node with no shards on it. So what we want to do is we want to scale the number of replicas for the index. And then we just add another shard, and then we can scale up and actually utilize the nodes. And this we can of course do until we hit the boundary, which would be minimum number of shards per node, and the maximum pods replicas that we can scale to. Just to show that this actually works in production, so this is over 7 days. The green and orange is like the CPU usage, so we can scale based on CPU. This fits into our use case. And the blue line is the number of replicas or number of pods in this particular. So this is only showing DE, Germany, so only one of these Elasticsearch datasets. So only a subset of the whole cluster, but it scales for from 22 or so to 44 or 45. And the reason that it here is so steep, you can see it when I zoom in here. You can see the scale up. It looks for some time, okay, the CPU is over a certain threshold, and then it scales up by a lot. This is because we basically have a case where we are duplicating the replicas, because this is how it's configured to scale in our case. And then later on, after people have looked at all the things and shopped during the evening, then it starts to scale down slowly, and you can actually see it scales down within 1 hour or so back to the lower limit that we have configured. And this way we saving, instead of running with the high line of 44 every time all the week, we are running most of the time with only 22 or so. So what are some of the lessons learned and takeaways? I think that like if you have all these bash scripts lying around for operating all your stateful things, turn them into operators. I think there's a cost up front of building an operator, but in the long run, it's really deserved because you move a lot of manual effort away from yourself and can focus on other things. Of course, if you have an Elasticsearch cluster of 3 nodes only storing logs, and it's okay if it's unavailable for a little time, then maybe you don't need this. But if you have a bigger setup, then I think it's definitely the way to go. And Kubernetes is one way to do it. You can also implement all these things in AWS or Google Cloud without Kubernetes, I think. But I think Kubernetes just makes it much easier because you have this API. You have, like if you use the stateful set, like we do, you get all this volume claim support and all these things out of the box. So you get a lot of things for free that you don't actually have to implement. And Another thing that we also like learned, or that I kept like saying to the other people in the team, is like assume the operator can die at any point. When you're writing the code, it's like easy to say, okay, we just need to put something in Elasticsearch via the API, then we store this here in a local variable in our Go program, and then we do the next thing. But if the operator dies because the cluster is scaling down and it has to move the operator pod, then you are losing the state. So always do things where you store the state on the custom resource or wherever, but store the state somewhere outside of the operator every time you do something, so it can always come back and continue where it left off. This is very important, and have this in mind when you're writing the code. I also think, like, maybe this is a personal opinion, but start simple and add abstractions only when you need it. So we started with the stateful set BeZero, where we tried to just use that. This was too simple. And then we like identified why we needed this abstraction. We needed to have the replica stored somewhere else, and we needed to be able to update the resource without affecting the existing replicas and like starting the thing to scale up and down unexpectedly. We might add like an abstraction later on that makes it simpler to just define an Elasticsearch cluster and get things out of the box. Right now you have to deploy the master yourself, just a deployment of stateful set. It's not that hard, but it is like an effort from the user point of view. And this we could maybe abstract in the future. But this was not our goal. Our goal was to like make all this bash scripts and so on encoded into an operator, so we don't have to do so much about scaling and updating and so on. Lastly, I just want to mention some of our open source projects. So Elasticsearch operator is obviously one. Kubernetes on AWS is where we run, is our configuration for our Kubernetes production clusters. So this is how we configure all our clusters. You can get inspired by this. We also have Postgres operator. And I think like Elasticsearch operator is much simpler because you don't have this like single master that you have in Postgres. So it's a much simpler problem to solve. And I think it also applies to like I said, Cassandra and Kafka and other things. And then we recently have, one of my colleagues released a Python Kubernetes operator framework. So normally most of the things are in Go. Our Elasticsearch operator is also in Go, but his team was using Python, so they developed a like Pythonic framework called Kopf. And this is like a very nice little framework that abstracts a lot of things away, so you can like just a few functions in Python code, then you can write an operator and it takes care of managing events and handling the custom resources and all this for you. So it's quite interesting also. I think you should check it out. And that's it. Thank you very much for attending.
Yeah, we have 10 minutes for questions. Anybody? Oh.
I have a question regarding the scale in and scale out. The scale in and scale out are relevant only to the pods, right? You are not scaling down and up the Kubernetes cluster as well. I mean, if I will run a Kubernetes cluster based on EC2, then it will scale only the pods, but not the cluster. The EC2 will still be running.
Yeah, so we use a cluster autoscaler in the clusters. So if the pods demand for pods are less than what the cluster provides of resources, then it will scale down. But obviously it will not force the Elasticsearch cluster to scale down. So it's only when, if you scale down the Elasticsearch cluster, then the nodes might also be scaled down underneath the EC2 instances.
Okay, thank you.
Hi, did you have any solution to safely shut down and start up the Elasticsearch?
So the question is, if I solution for safely
with an operator, did you implement any logic if you have a distributed Elasticsearch cluster to stop and start it properly? Because if you kill one of the nodes, usually it starts replicating to the others.
Yeah, so what do you mean, like turning down the whole cluster and then bringing it back up?
If you're starting and stopping.
No, this we don't have. We haven't had. We don't have this use case, but I mean maybe it's feel free to open issues on our open source repository if you need something that we didn't think about.
So thanks for the talk. It was really interesting. You explained how you did it. I was actually wondering very much the reason why you did it. I mean, as you said earlier, you could do the same using some EC2 instances. You decided to implement an operator to manage it on Kubernetes. It's a lot of effort. So, I mean, I'm sure you had very good reason to take this choice. What are these good reasons, and do you validate them?
So, like I said, that we declared Kubernetes the default deployment target, and this is for the whole organization for several reasons. One thing is that we have like a CI/CD system that is integrated with Kubernetes and is much easier to use and is much like nicer for our developers to deploy against Kubernetes than what we had before. So it's like one of the reasons that we are moving to Kubernetes. This also like automatically means that it makes sense to actually try to run these workloads. You could say Elasticsearch is stateful set or stateful application. It's more difficult, but they were kind of needing this anyway. They were managing it, but it wasn't like sufficient. They used a lot of time on managing it manually, so they needed to implement something like this anyway. And like I said, I think Kubernetes just provides a lot of the features out of the box that makes it easier. So yeah, and by having this, we can also like offer it to the open source community. Other people can benefit from it. We can improve it. I think also like a lot of the code is so abstracted in the Go code that it can be used also to implement an operator for Cassandra or something. We haven't ventured there yet, but I think it's possible. So these are some of the side effects. I mean, in the end, it's kind of the organization going this way, and I think there's good reasons for it, but yeah, it could also be done other ways, but yeah.
Okay.
Hi there. I realised this was only announced yesterday, but I wondered whether you'd had an opportunity to compare Elastic's own operator against.
No, unfortunately not. I have not. We have been a little bit talk. I have not been so much involved, but I haven't seen it at all yet, so I cannot comment at all on this.
Thank you.
Hi, I would be interested in how large are these Elasticsearch data sets? When you scale them up and down, how much data is moved around?
Yeah, this is actually good questions that I don't know the answer to. So I said in the beginning that I'm not so much on the Elasticsearch side, and I also don't manage this now, so I actually don't know. Oliver Trosian from from Zalando is the one to ask. I can tweet about him, and then you can ask this way. He would know it.
Any other questions?
How many clusters are managed by one operator, and how do you handle the relationship between the two?
Essentially, it can manage any number of clusters. You have to deploy the masters yourself. So depending on how you configure the Elasticsearch datasets to connect to which master, be part of which cluster. But the operator doesn't really care about this. It cares about the datasets, and they each have a service that is pointing into the cluster they are part of. So it can operate any number. You can also limit it to a certain namespace, and you can also limit it to just a single Elasticsearch dataset that has a certain annotation that means only control this one. So you can also run multiple controllers and operators, and they will not like interfere with each other. But there's no like rules for this. You can do it how you want, how you see fit. I cannot hear you.
Have you run into any scalability issues, sort of that the operator didn't manage to sort of handle all the clusters it had to manage?
So
because
we have
of the
been running it
reconciliation?
for around, the question is if we hit any scalability issues. We've been running it in production for around 3 weeks. And we had one issue, which was that we reached the limit of our overlay network size in the Kubernetes cluster. So it wasn't really because of the operator. but it meant that we basically had to reduce the number of IPs we allocate to each node so we could get more IP space. This was kind of interesting to see. It didn't really have an impact because it just meant new nodes didn't come up, but we haven't seen anything. Like, obviously we have fixed issues along the way, but since production we haven't seen issues with this auto-scaling of the Elasticsearch itself.
Hi. Have you heard probably about the CoopDB operator on the market? They operate actually a lot of different storages, like Elasticsearch as well. If so, do you have any like plan to merge feature sets between these two operators to like to leverage both operators' experience into one?
I think, and correct me if I'm wrong, I think the approach is a little bit different in the way that I see that they take it more from the abstraction point of view. That's how I see it, that they like try to make it nice for the users and you just have a simple definition and you just get a full cluster out of this. And we kind of approached it in my mind from the other side where we try to first fix all the like operating, the hard parts of operating it, especially for our use case. And we haven't focused on like making it super easy to just go to our page and just deploy via one simple YAML file. So this would be like the things where we could maybe converge. But yeah, we haven't looked so much into it. But when we looked around for something before we developed our own, there wasn't really something that did what we wanted it to do on the operation sides, on the heavy lifting there.
Question. How is operator one per namespace, or you have namespace for operator and different clusters in different namespaces?
You can run it however you like. You can say either one operator can only touch this namespace where it's running, or you can control with ABAC roles what it gets access to. We run it just like in the cluster, and then it can like manage any number of Elasticsearch clusters within this Kubernetes cluster. But okay, you can do how you want.
But you can run one per namespace.
Yeah, we have one just for the whole cluster, and then it just manages no matter the namespace. Because we don't like restrict the namespace in our setup.
But it is quite dangerous because if you want to have one operator for all namespaces, update of operator can break the databases in all namespaces.
Yeah, that's true. That's worth considering.
I think we might have time for one more short question. Anybody have one? All right, in that case, thank you very much, Mikkel. Yeah. And don't forget to please rate it on the app. Thank you.
Thank you.